I'd give it a bit of time.
We will wait another 2 minutes before we start. Welcome everyone for the keynote lecture of the 2025 Astronomy Open Night. Lovely that you're all here, particularly that we have so many kids in the audience. So from the very young to the very old, we are excited to learn much more on the noises the universe makes. And it is my great pleasure to introduce our keynote lecturer for the night, the wonderful Associate Professor Jo Dawson. Jo is a radio astronomer working here at Macquarie University and CSIRO's Australia Telescope National Facility. She did her undergraduate degree in astrophysics at University College London, her PhD in Nagoya University, Japan, and worked as a researcher at University of Tasmania and CSIRO before coming to Macquarie in 2014. Associate Professor Dawson uses radar telescopes in Australia and the world to map the ultra-diffuse clouds of gas and dust between the stars, including enormous superbubbles, hundreds of light years across, blown by the dying explosions of the most massive stars. It's a privilege to serve the Faculty of Science and Engineering as the Executive Dean. My name is Sam Muller, and Jo is one of many wonderful academics I have the privilege having in the faculty. Over to you, Jo.
Thank you, Sam. All right, thank you, Sam, and thank you, everybody, for coming. I'm going to start by turning the lights down. So, hopefully that all looks appropriately beautiful to you now, and hopefully you don't get too sleepy. So I'm here today to talk to you about an invisible universe. So this is a universe we can't see with our eyes at all, but which contains some of the most energetic phenomena known to mankind, as well as some of the gentlest and most chilled out processes we know about in the universe. We've known about this universe for 100 years, and yet all of the light we've collected to make images like this amounts to less energy than a few snowflakes striking the ground. So how is this possible? So everything you're seeing here now is not an image made with visible light, but it's an image made with radio waves. And so that is the longest wavelengths of the electromagnetic spectrum. So when you hear about radio, I imagine that for most people, this is the kind of association that comes to mind straight away. You think about listening, you think about recording, you think about broadcasting. If you're as old as me, I do remember old analog radios, and some of you probably do too. So clearly this is not what we're talking about. This is Astronomy Open Night. We're talking about radio astronomy. If you have an image in mind for radio astronomy, it's probably something more like this. This is an iconic scene from the movie Contact. There's Jodie Foster there, listening to this signal from space being picked up by this array of radio dishes over there. Now, this picture's partly right. This part is fine. We do indeed, this is exactly the kind of instrument we use when we're doing radio astronomy. This part, no, is wrong. Despite the artistic license I took with the title of the talk, radio astronomy has nothing to do with listening. It's everything to do with looking. And the reason for that is radio waves are just like light. It's all the same stuff. It's part of the electromagnetic spectrum. So that is an oscillation of an electric or magnetic field propagating through space. The only thing that is special about visible light is it's the part of this spectrum that our eyes are sensitive to. So visible light has wavelengths of somewhere between about 400 and 700 nanometers. To give you a bit of scale, that's a little bit bigger than a flu virus and a little bit smaller than a red blood cell. Radio waves are up to 1 million or more times longer than that, a few millimeters and larger. And I want to point out here that as radio astronomers, we claim the microwave part of the spectrum for ourselves as well. To us, this is radio. And that means when I say radio astronomy, we're talking wavelengths of a few millimeters, like the size of an ant, a few meters, the size of an elephant. Most of the radio waves we receive from space are in this wavelength range, but there's no reason they can't be bigger. It goes on almost infinitely. There will be radio waves the size of the Earth. We just haven't got the technology to detect them yet. And when you look at the sky in radio, it looks really different. So here is a normal optical image, a visible light image of the sky. You're seeing the Milky Way along the center of the image. I've oriented it so that we've peeled out the whole sky and we've stuck it on the page such that the plane of our Milky Way galaxy is running along the center of the image. And you'll recall that we see the Milky Way as a band of light because that's the view of our own spiral galaxy from our position within it. So we're embedded in the Milky Way, somewhere far out from the center. It's a thin disk of stars and dust. And when you project it onto the sky, the view we have is this dusty band of starlight across the middle of the sky. So that's what you're seeing when you look up at the sky and you see the Milky Way. This is a view towards the center of our own Milky Way galaxy. And everything you're seeing here is stars, or it's the dust, the vast clouds of dust and gas that are absorbing that starlight. Zooming in too, every little dot you see here, it's not scruff on the image, it's a star. And everything you see here in this cloudy black stuff is the dust blocking our view towards the center of the Milky Way, because you can only see so far with visible light. The dust and the other stars obscure everything. However, if we take just this center region and we zoom in further and we now look in radio waves, you see something quite spectacular. The stars are gone, the dust is transparent. And now what we're seeing here is peering towards the very center of our Milky Way galaxy, 25,000 light years away. And there is a huge amount going on in this image. This image is famous, it's iconic, it was made a few years ago by the Meerkat telescope in South Africa. Let me just tell you some of the things you're seeing here. So where you see bubbles like that, these kind of bubbly structures, these are supernova remnants. These are the remnants left behind when a high-mass star has had a cataclysmic explosion and died. But what you're seeing here in some of these regions are some of the most active places of young stellar birth. So you've got stellar death, and you've got new stars forming in these clouds here. These crazy-looking filaments you see crisscrossing the image vertically, those are real features, and we actually don't know entirely what they are yet. These are pretty famous, they're called radio filaments. We know that it's something to do with the magnetic fields that thread through the center of our galaxy. And we know that it's something to do with charged particles moving in those magnetic fields, but it's still an open question. And when you look at this sort of flower-like structure in the middle, this is peering into the chaotic region around our Milky Way's supermassive black hole. It's a 4 million solar mass black hole buried deep in the heart of our galaxy. And that's what you can see in radio. So just this slide alone, which is just a small portion of our own Milky Way galaxy, should already give you a sense of the vast array of physical processes that open up to us once we look not in visible light, but in radio waves. And so this talk, I'm going to take you on a bit of a tour of some of them. But there is so much that radio astronomy has done for us, and so many processes that we can see here that we haven't been able to see in other ways. And it would be impossible for me to talk about all of them. So I'm going to focus in on some of the most iconic and spend a little bit of time on each in this talk. I'll start with supermassive black holes. We'll talk a bit about pulsars. We'll move on to atomic hydrogen. And I'll end up by telling you a little bit about the technology that we use to observe this stuff. So to start with, this is an image of the whole sky now, not anymore in visible light, but in radio waves. Now, the image is pretty fuzzy. Don't let that bother you too much. That's just a feature of this particular telescope that took this image. It's pretty small. This is radio waves that are about 1 meter in length, and this is what the entire sky looks like. And I've done this partly so that you can see that most of what we see on the sky is clearly coming from our own galaxy. You can tell that because there's the Milky Way going across the center of the image. And this stuff arcing up the top is very close by to us as well. Now, if I then change the contrast on this image, so that I can only now show the really brightest sources on the sky, you see just a couple of dots jump out. Alongside our center of the Milky Way, where the black hole is, you see a couple of others. And I want to start by talking about this one. This is Cygnus A, the brightest radio source in the sky, except for the sun, which is not in this picture. not pictured here. So Cygnus A is by far outshining almost anything else on the sky. So let's take a look at this part of the sky in visible light. And this is the image we see. So what you see in the center here, this little smudge, is a far distant elliptical galaxy. Doesn't look like a huge amount in visible light. The stars here are foreground stars. They've got nothing to do with the galaxy itself. This is the bit we're interested in. Now, if you move away from visible light and move into the radio, this is what you see. You see something quite spectacular and quite different. You see a little tiny bright dot in the middle, and you see these needle-like jets coming out of it, ending in these big, puffy, gaseous lobes. So the length of this thing is crazy. This galaxy is 700 and something million light years away. That is 300 times further, I'm checking my notes, than the Andromeda galaxy, which is the most closest big galaxy to us. And the length of these radio lobes, as we call them, is about 3 times the size of our own Milky Way. So this is really big. So taking a bit of a closer look now, this is the radio image again. It's a different false coloring, but it's the same thing. And now we're going to zoom in, and we're going to zoom in about as far as we can with our current technology. So we're looking in at the central portions of that jet. That thing that looks like a dot here gets elongated. And as we zoom in further and further, we start to see that almost as far as we can look, the thing's really thin. So now our scale here is 2 light years. Remembering that the length of this jet the length of the whole structure was 300,000 light years. So you've got this incredibly sort of hair-thin point of origin blowing out into these big lobes. I'll point out now, this stands for Very Long Baseline Interferometry. This is the technique we use to make these images, and I'll talk about it briefly later on. But for the moment, the thing we want to think about is what on earth could be doing this? Well, I gave it away a little in my content of the talk, and the answer is a supermassive black hole. So a supermassive black hole, 2.5 billion times our sun's mass, lurks in the center of this galaxy. This is an artist's impression, of course. I've tried to indicate clearly wherever that's the case. And this is an artist's impression of the matter from the parent galaxy swirling into an accretion disk around that black hole where it's getting heated up to really high temperatures. And this black hole, that process is shooting out jets of ultra-fast particles from each end. And that's what we see as those radio jets. So I wanted to show you a bit more about how this works. And this is a supercomputer model of the process of black hole jet formation. So everything here is false colored, everything here is done in a supercomputer, but it's done to model the process of how this works and how the jets form. So this is a zoomed out image around a black hole as the jets begin to shoot out of it. The stuff you can see here is the rapidly spinning accreting material. And what I want you to look at is the little magenta lines that are drawn on. These are drawn on to represent the magnetic field. As this thing spins around furiously fast, it tangles up these magnetic field lines that shoot out of its poles. And along those field lines, particles get caught up and swept up and accelerated to close to the speed of light, where they shoot out in those jets. And as they do so, they curve around a little bit around those magnetic field lines, quite a gentle thing relative to their incredible speed. And that gentle curvature is what gives us the radio waves. They lose just a tiny fraction of that immense energy to radio, and that's what we see. So in fact, what we're seeing here now, just to look at this image again, is we're seeing these jets of relativistic charged particles shooting out of that supermassive black hole that's buried right deeply in there. It's very small, impossible to see on this image. And what you're seeing, the reason they form these gaseous lobes at the end, is they are in fact impacting on the gas surrounding this galaxy. There's gas in between galaxies. It's invisible here, it's also invisible in the radio in this case. But where it lights up is where those relativistic jets have deposited all of their energy into the surrounding medium, causing it to glow. So what you see here, it looks like, clouds, but actually it's cavities. It's cavities filled with very hot, very rarefied gas that's been kind of carved out of this intergalactic medium. And in this particular case, Cygnus A has a really nice X-ray cocoon as well. In this case, the X-rays are also marking really hot gas, but they're marking the past influence of the jets. because the jets can change direction over time and they can hollow out different parts, and it has hollowed out this kind of cocoon, hundreds of thousands of light years wide. Now, Cygnus A isn't the only example of its kind on the sky. It's the brightest, but it's just one of many. Centaurus A that I'm showing you here has the distinction of being the largest. So I'm going to show you now a little video of that. So we're going to show the scale of this is the optical galaxy in the center of Centaurus A. And soon we'll be zooming, so now it's shown to scale with the moon. And that is the scale of the radio jets. They stretch many degrees on the sky. And this one's pretty bright too. If you could see the sky in radio, you'd see this stretching across the sky, much larger than the moon. So almost all galaxies that are large, like our Milky Way, have a supermassive black hole at the center. That means that there are countless billions of galaxies doing similar things throughout the universe. Not all of the black holes are consuming matter and shooting out jets. Some of them are resting. But those that are, we see like this. And we already know tens of thousands on the sky, and those are just the ones that we can catalog. So what about our Milky Way supermassive black hole? I mentioned that it has one, and it does. Our Milky Way supermassive black hole is a relative baby. It is only about 4 million masses of the sun, rather than 2.5 billion. And it's sleeping right now. It's not got a crazy accretion disk like this. It's not chewing through matter. It's not spewing out jets. What it does have going for it, though, is that it's close. And if it's close, we can get a good look at it. So this image may not look like much, right? Maybe it's a bit of an anticlimax, so after all that zoom through, you've got an orange blob. However, I cannot stress hard enough how amazing this image is. This is one of the first, it's only one of two images, direct images of black holes that we have. What's actually happening underneath there is something like this. This is a model of the system that we've observed. We've pushed the resolution, the absolute resolution limits of our telescope, and we've just managed to image it. We've just managed to image what's called the black hole shadow. This you're seeing here is the accretion disk, our small accretion disk around our little baby supermassive black hole, warped by the intense gravity of the black hole itself, and we're getting very close to the event horizon. The event horizon is somewhere in here. And just to give you, again, a sense of how incredible this piece of imaging is, the scale you're seeing here is 50 micro-arc seconds. That is 100 millionth of a degree of arc on the sky. The resolution we can take with this radio telescope image is 100 times better than the best resolution of the best optical telescope that is yet to be built, that is still under construction. The scale we're looking at here is 60 million kilometers, 25,000 light years away. This is like putting an orange on the moon and seeing it from Earth. It's a really incredible piece of science. And it's the scale of about Mercury's orbit, so we're seeing tiny and very far away. And I will return to how we do this in the end of my talk. But for the moment, because this is a quick tour of the universe, we're going to move on. And we're going to move on from supermassive black holes, and we're going to start on pulsars. So, I told you that radio astronomy was not about listening, and I stand by that. That is very true, but there are some times when it is useful to sonify the signals we get from space, to turn them into sound. And pulsars are one of those rare occasions where that is the case. Hopefully you can hear this. I'm going to turn it up. This is a cosmic signal. This is coming in from space. This is the pulsar 1933 plus 16, observed by the Jodrell Bank telescope in Manchester, UK. This plot you're seeing is the intensity of the radio waves. This is time. This is clicking in incredibly regularly at just under 3 pulses per second. This scruff you see along the bottom is the background noise from the sky and from the telescope itself. But these pulses are real. This is a fast one. This is the Vela pulsar, observed by the Parkes telescope in Australia. This is around 11 pulses per second. And like, mind your ears, this one is one of the fastest pulsars we know. This is not noise anymore, this is pulses squashed together. This is around 175 pulses per second. And I'm going to turn it on because it sounds horrible. Turn it off because it sounds horrible. But this is a pretty incredible thing. These signals we receive from space are some of the most precisely measured signals known to man. We can predict the arrival time of a pulsar pulsar within nanoseconds. So much so that the most accurately timed pulsars can keep time better than the world's atomic clocks. And I'm showing you this beautiful picture of a church here because there is a place where we have done just that, and we have built a pulsar clock. And that is St. Catherine's Church in Gdansk in Poland. This is the roof of the church. This is a little bunch of radio antennas. And this is the clock. So how on earth is this possible? How are these signals coming in from space that are so precise and that we can measure so accurately? It was a mystery for a while, to the point where when these were first discovered in 1967 by Dame Jocelyn Bell Burnell, the first thought that people had was like, is it aliens? Because you would. But I can assure you there is a perfectly natural explanation. And that a natural explanation is neutron stars. So these incredibly precise blips of radio emission that we see are coming from rotating neutron stars. That's super dense, super magnetized, furiously spinning little dense balls of stuff. And as they rotate, they send out these beams of radio waves along their magnetic poles. And they sweep along, and if those happen to kind of coincide with our line of sight, we get a bright flash in radio, which we measure as a pulse. So this is happening because neutron stars are spinning so fast and their magnetic fields are so strong that they generate an incredibly powerful electric field that shreds atoms, accelerates electrons to near light speed, and so those electrons get accelerated within the magnetic field of the pulsar. You're seeing magnetic field lines here. Where the field lines are closed, the electrons are trapped. Where the field lines are open at the magnetic poles, they stream out, and they emit radio waves much in the same way as the black hole jets do, just in a slightly different system. Oops. So to understand a bit more about how this comes to be, we need to understand how neutron stars come to be. So neutron stars are the super dense, super magnetized remnant cores of a dead massive star. It's a zombie star. It's what's left when a star dies. When a really massive star dies, it dies as a supernova explosion. It implodes inwards. The rebound explosion scatters most of its stuff back out into space, but the core remains ultra condensed, and that's a neutron star. So neutron stars have some pretty mad properties. This is a pretty typical example, obviously not a real picture of a neutron star, floating above Sydney. 1.4 times the mass of the sun is a pretty small neutron star, squashed into about a 10-kilometer radius. So to give you an idea of just how ridiculous this is and how sort of beyond our comprehension this is, 1 teaspoon of neutron star matter would weigh like 10 million tons. That's like more than all of humanity squashed into it. If you took all the humans on the Earth and squashed them down, you'd get 1 teaspoon of neutron star matter. It's like a super compressed particle soup where the normal laws of physics don't even apply. We don't even really understand what the state of matter is inside a neutron star. And this incredible density and this incredible sort of compression of matter into a small space is also the answer to why they can spin so fast. So this is due to something called the conservation of angular momentum, a bit of physics for you here. It's a fundamental law of the universe that if you take some stuff that is spinning and you bring that stuff inwards into a smaller volume, a smaller radius, it starts spinning faster. So this is an example that you will have seen, even if you didn't recognize it at the time. The ice skater, when she's got her arms out, when her mass is spread over a larger volume, she's spinning slowly. And as she brings her mass inwards to a tighter radius, she spins up without putting any more energy in. So you can appreciate that even just over these small scales where she's brought her mass in just a little bit, she's spun up quite a lot. So when you form a neutron star, it's like that process on steroids. You have a pre-collapsed stellar core. It's kind of Earth-sized, spinning kind of gently. And you start with that. You implode all of its mass in, and you end up with a neutron star, which is so small that I couldn't even draw it on here if I was drawing it to scale. It would be below the pixel scale of this projector. But all of that spin has been conserved. So the thing can now spin many times per second. But even that is not enough to explain the fastest spinning pulsars we see. So the ones like the really fast one I showed you before, that's spun up by getting even more spinning mass onto itself. And the way it can do that is by cannibalizing another star. So here's a neutron star, a new pulsar in a binary system. When its companion star grows to be a supergiant, it starts siphoning off mass, which spins into this accretion disk. And as that mass spirals inwards, it retains its angular momentum. And that initial first pulsar has used it to spin itself up. Now in this particular animation, that pulsar is still really slow, relatively speaking. As we saw, the fast ones can go hundreds of times per second, which is really quite incredible when you think of it. And also, the reason they don't smash apart going that fast is because of their incredible density. So I'm going to move on from pulsars again. I told you it was going to be a quick tour. But one thing I do want to say is an incredible thing about pulsars is not just studying them for their own physics, but it's about what we can do with them. Because it turns out there is a lot you can do when you have an incredibly accurate clock out in space. And one of the things we can do is use them as gravitational wave detectors, and I will tell you very briefly how. So you may be familiar with the idea of gravitational waves, that is warping in space-time itself. This cartoon shows you two black holes in-spiraling and generating ringing gravitational waves as they merge. This is like dropping a single stone into a pond. However, this kind of thing is going on all the time. Every supermassive black hole in every galaxy that we see can merge with another galaxy, and the black holes in them can merge. When you have that, you have many stones being dropped into the pond that is space-time, and you get this kind of chaotic, ripply background. We call it the gravitational wave background. And when you merge supermassive black holes, the scale of galaxies, those gravitational waves you get are really long. These are galaxy scale, kind of interstellar scale gravitational waves. This is nothing we could detect with a detector on Earth. The stretching of space-time is just too slow and too long. But you can detect it when you have a bunch of clocks with very precisely measured signals sitting in all kinds of different places on that choppy gravitational wave background. And I will leave it here because this could be 2 talks all on its own. But I'd encourage you to come up to the Central Courtyard Scientist Spotlight area later, where we are doing live observations of pulsars with the Parkes Radio Telescope. And we also, my young colleague who's sitting in the audience at the front, is working on studying gravitational waves, and he will tell you all about this. But moving on again, next stop, atomic hydrogen. So this is the emission from atoms of hydrogen in interstellar space. They're just hydrogen atoms. They're sitting there very chill. They're not being smashed into bits. They're not being accelerating to light. They're not accelerating to light speed. They're not being thrown out of a jet. They're pretty much just sitting there doing very little on human timescales. But there's something special about the radio waves we're seeing from this particular gaseous cloud, from any cloud of hydrogen. And that is that they're all one color. They're all a single wavelength. Everything I've told you so far today, the radio waves we can receive from those processes are broadband. They're multicolored. It's like white light. This is like a single tone of red light, all coming from these hydrogen atoms. And how is that possible? So to understand why, let's have a closer look at hydrogen. Hydrogen's the simplest element in the universe, just one proton, just one electron. Those protons and electrons have something called spin. They're basically rotating. Sometimes they're rotating the same direction, sometimes opposite directions. So it turns out that if you have a hydrogen atom like this, just sitting there doing its thing, every so often something completely spontaneous will happen. And this is what will happen. You'll have a spin flip. suddenly, without warning, that electron is going to spin the opposite direction. This is the magic of quantum mechanics. When it does this, it will lose a very specific amount of energy, always the same amount, and it will emit that as a radio wave. And because it always loses the same energy, the radio wave always has exactly the same wavelength. That is 21.1 centimeters, about so big. So I told you that I was going to tell you about some of the most chilled out processes in the universe, and the spin flip is one of them. If you were to take a hydrogen atom and just watch it, not do anything else to it, and wait for it to flip, it would take on average 12 billion years to do so. So it's not in a hurry. So you may think this means, well, why on earth are we seeing this then? Well, the answer is simply that there is a lot of hydrogen in the universe. So if you were to split the normal matter of the universe up, you would find that the vast majority of it is hydrogen. And that's good for us, because it means that there's trillions and trillions of atoms of hydrogen sitting there, and on average, some of them are always doing that spin flip. And so this is good for us. We know exactly what wavelengths to look at. We can tune our telescopes to exactly that wavelength, and if we did so, I'll show you what we would see. I'll try to. So all the emission you saw from the sky in that video was, again, mostly coming from our own Milky Way, covering the entire sky because we're embedded within it. The spinning, I should point out, just for the sake of accuracy, is to mimic the spin of the Earth. It would not be moving on the sky like that. You wouldn't even see it. It doesn't change over human lifetimes. Neither do you see it move across the sky, nor do you see it change shape. But this comes from our Milky Way, and our Milky Way is not special. So this is M33, another spiral galaxy, a lot like our Milky Way. Now, by this point, you can probably guess where I'm going. This is a visible light picture of M33. And overlaid here in blue is what you see when you look at exactly 21 centimeters in the radio. So this galaxy disk is far larger than it looks. The bit you see in visible light is only part of the picture. There's gas extending way further out. And the gas like this in a galaxy is a kind of cosmic fuel. This is the stuff from which stars are made and to which stars return a lot of their mass when they die. Now, there's something else special about being able to see radio waves in just one color and to know exactly what color they should be. And that's that you can then start to tell how things are moving. And let me tell you why that is. So this is to do with the Doppler effect. So I'm going to imagine that this source here is emitting radio waves. It could be anything, it could be light, but let's make it radio waves. The distance between the peaks of these radio waves is exactly 21.1061 centimeters. I've drawn it like ripples on a pond here, but you could just as easily draw your kind of classic wave ripple. This is what's coming from our hydrogen gas. Now let's try moving it. And now let's put the Earth on one side here, and let's put another Earth on this side here. So what I want you to notice is, although the wavelength that it's emitting hasn't changed, the motion's done something. On the side where it's approaching us, the wave has been squashed up. On the side where it's receding from us, the waves have been spaced out. And we call this redshift. When the wavelength is longer, in visible light, longer wavelengths means redder light, so we call it redshifting. And when the waves have been squashed together, and the wavelengths are shorter, we call it blue shifting. Now, in reality, the effect is way smaller than I'm showing here. This is greatly exaggerated. If I was to take a gas cloud of hydrogen and to fling it away from us at 100 kilometers per second, I would get a wavelength change of 1 millimeter in my measurable radio waves. But that's fine. Like, we can measure that. Radio telescopes have the technology to do that. And so now if I go back to my picture of M33, but now I color code that hydrogen gas by how it's moving, I see that on one side it's red shifted, and on the other side it's blue shifted. So how do you produce this kind of structure on the sky where one side of it's coming towards you and the other side of it's coming away from you? Well, the answer is rotation. The answer is that the galaxy is rotating. And we can find direct evidence of that from looking in radio. So, and that's been an incredibly powerful thing, and one of the most direct pieces of evidence for dark matter is the fact that we're able to measure how galaxies rotate. We can do it for our Milky Way, we can do it for external galaxies as well. I won't spend long on this graph, but the thing to look at is that we can do some of these observations from starlight. This is the distance out from the center of a galaxy, but as we get further out, there is no more starlight. In order to measure this properly, we turn to our 21 centimeter hydrogen emission. And that gives us this beautiful rotation curve of M33, which, as anyone will know if they've learned about dark matter, is going way faster than it should do. This is what we think it should go if you can just, this is the spin that it should have if we just add up all the matter we can see in radio or optical or anything. And this is how fast it's really going, which tells us there's a great amount of dark matter inside it. We can also use the motion of the hydrogen gas to learn about other things too. So this again is now a view of our Milky Way again. The picture underlying there is another optical picture peeled out onto the sky. What you're seeing here in the pink is places where the hydrogen gas that spreads across the sky, so we know it's close to us if it spreads that big, it can't be far away, is not moving how it should be. It's moving much faster and is not moving with the rest of the galaxy. This is just the stuff that isn't moving with the rest of our Milky Way's gas. So what's going on with that? So if you're familiar with the sky at all, you may recognize that underneath this pink, you've got these two smudgy little things here. This is the Large Magellanic Cloud and the Small Magellanic Cloud. As they appear on the sky in visible wavelengths, you pretty much would only see those two smudges. But when you look at them in hydrogen, you get this whole stripped out tail of gas going across the whole sky. And the reason for this is that these galaxies are small satellite galaxies that are being cannibalized by our Milky Way. This is a model of some process like that in action. You can see a Milky Way-like galaxy. This is all gas now, forming at the center here. This is a satellite galaxy. That just came in was a satellite galaxy. And if you watch that thing fall in, you can see it get drawn out and completely shredded apart by the gravity of the Milky Way. Eventually, we think the Milky Way is going to consume the Large and Small Magellanic Clouds. And this goes on all the time, and in fact is pretty much how larger galaxies form, by cannibalizing the small ones. But by using the motion of the hydrogen gas, we can see that in action in our own Milky Way. So, moving on again, I told you this would be quick. We're moving on from atomic hydrogen, and now finally we're going to get to radio telescopes. So depending on how much you're into tech versus how much you're into space, this is either going to be the most exciting part or the most boring part of this talk. But, well, see how you go. So, how do we build telescopes to observe all this stuff I have just shown you? This may look very different to an optical telescope, but actually it's not so different. This big dish here is a mirror. It collects the radio waves from space and reflects them onto this subreflector here, where we detect them. Just like an optical telescope, the bigger the mirror, the more we can see, the more fine detail we can see, and the fainter sources we can see. This is the 64-meter Parkes Murray-Yang dish in New South Wales here. And again, let me plug this one more time. We have this telescope tonight. We are controlling the Parkes telescope. If you want to come and observe with Parkes, we're in the central courtyard, first floor. But we do have a problem. We can't go as big as we need to go. And that's because, if you recall, well, you may know that the bigger the telescope, the more fine detail you can see. With an optical telescope, we can build it pretty small, and you can see quite a lot. Even the telescopes out in the car park, you can see quite a lot of detail on the sky with something about the size of a human. But the longer the wavelength, the bigger the telescope you need to do the same thing. And radio is way up here, millions of times longer, and that means if we want to build a telescope that can see as well as this one, we have to make it like half the size of here to Newcastle. So this starts to get a little bit infeasible. To give you a bit of context, this is the largest single telescope we've currently built, named FAST, the 500-meter aperture spherical telescope. It's in China. They had to like evacuate an entire valley and build this thing in there. And it's so big and it's not steerable, right? It's a fixed structure. So you can't even point it at different places on the sky. You pretty much have to wait for the sky to come above it to see what you want to see. So this is a long way from our distance from here to Newcastle, though. So how on earth, then, are we getting pictures like this? This is your, which one was this one? Centaurus A galaxy again. On the left, for a bit of context, I pulled this data out a couple of days ago from arXiv. This is what Centaurus A looks like with Parkes, which is a pretty decently big dish. But even if we turned the FAST telescope on Centaurus A, we wouldn't get anywhere close to this quality. So then how have we done it? Now, the clue here is in the name. The Murchison Wide Field Array is the telescope that took this image. And that's because after a while, when we can't build big enough single telescopes, we try doing something different. We can do quite a clever trick. And that is we can build a vast array of telescopes, and we can combine them into one in the electronics. So this is the Meerkat telescope in South Africa. I'm going to embarrass myself by forgetting the number of dishes it has now, but it's close to 100 dishes. And it's this is the telescope that made that beautiful image of our galactic center that I showed you earlier in the talk. So the way this works, and I will show you this now with a picture of another telescope, top-down view of the Karl Jansky Very Large Array in the USA. In this one, we've built the telescopes in a Y shape. You don't need to. But it's a good illustration of my point. And that is when you build a radio interferometer like this, you get the resolving power of a dish as large as the two most furthest spaced elements of the array. So that seems pretty good. And in fact, you don't even need to build dishes. Once you're out combining things into a synthetic telescope, you can often do away with the dishes altogether, particularly at longer radio frequencies, longer wavelengths. This is a drone fly-through of the Murchison Wide Field Array, the telescope that took that glorious picture of Centaurus A. And this thing is made up entirely of these tiles of spider-like antennae. And you can go even further, and we have. You can build a telescope the size of the Earth. You can take individual elements in different countries, you can combine it all together in the electronics, and this is the telescope, the Event Horizon Telescope, that was responsible for this really disappointing looking but really scientifically amazing picture of our Milky Way supermassive black hole. So then what's the catch, I hear you ask? Because of course there is one. And put very simply, you can't get something for nothing. However much you might wish that you have built a telescope the size of the Earth, it is not, in fact, a telescope the size of the Earth. There's a bunch of little telescopes, and you miss a lot of information. Just to give you some idea of sort of how that looks when we haven't got a perfect instrument. This is a synthetic image I made of Centaurus A. In fact, using the radio interferometry demo that you can also experience up in Central Courtyard on the first floor. This is what happens when I try to observe it, essentially with not enough dishes. It doesn't look right at all, right? Like there's something very wrong with this picture. If I now put a whole bunch of dishes together, but I've spaced them too far apart, something different is happening here. In fact, I mean, it looks like rubbish at first, but if you look closely, you've actually picked out some stuff that is real. This little dot in the middle here, that's the nucleus where the supermassive black hole is. And these little details around the edge are the detailed edges of these jets. So when you space things too far apart, you get the detail, but you miss the big picture. And so then I made something that was a bit of a nicer array, a bit more realistic, a bit more like what the state of the art can do today. And even then, it looks kind of janky. And this, without going into any of the technical details of why this is, should give you a sense that it's actually not easy. We have a lot of clever modeling and processing to take something that pops out like this and be sure that we are really seeing something like this on the sky. And in fact, the Event Horizon Telescope black hole one is a good example. It was incredibly difficult to make that blobby image because they've spaced their telescopes so far, they are missing so much information. They had to do some very kind of inspired reconstruction of what was under there. Our other problem is we may have the resolving power of a dish this big, but it's actually only made of these little green spots here. So we only have the collecting area of a dish this big. So we can't get as deep or as sensitive as we might expect. However, interferometers are getting bigger and better all the time. This is an example of one of the state-of-the-art instruments here in Australia. This is CSIRO's ASCAP telescope out in Western Australia. This has 36 dishes. Something that's special about ASCAP is that rather than they have radio cameras on ASCAP. I skipped over this before, but with radio telescopes, we actually don't even have cameras. We have a single pixel. It's like if I want to map my sky, I have to point at one bit. I got that pixel, then I got to move and get another pixel. ASCAP has radio cameras, so tech is coming along all the time, and those were designed at CSIRO here in Australia. So before I wrap up my talk, I want to leave you with a bit of a forward-looking outlook. And that's on the topic of the SKAO. It's going to be the world's largest telescope. It's currently under construction in South Africa on the site where the Meerkat telescope was. In fact, it will subsume Meerkat inside itself. And again in Australia and Western Australia. It's actually 2 telescopes. It's an array of dishes. It's an array of nearly 200 dishes and nearly 130,000 individual antennas here in Australia. And it's a global mega project. When you get things this big, it's no longer the work of one institute or even one country. It's the work of the world working together, and governments have signed treaties for this. And to end us on a high note, I'm going to show you a video from the SKAO of the progress that was made on this project over the last year. So I should say, if this was exciting, hopefully it was exciting, you should be excited, because this is coming. We've been doing this for decades, building this thing, and it is finally about to come online. And I should say to you, anyone who's in the audience thinking about what they want to do with their lives going forward, there's probably no better time to start learning radio astronomy, because this thing will be coming, and this is where the excitement will be. So thank you very much.
Thank you very much for an awesome talk, Associate Professor Jo Dawson. We have time for one question, and then I know many of us need to go to a 9 o'clock event. We can take one question.
You can come up to Central Courtyard and ask us loads of questions. We're there for another hour. We need a mic. Oh, yeah.
Can the magnetic poles on a pulsar switch like the Earth's can?
I've never heard of a pulsar switching its magnetic orientation, is my answer to that. I don't think so. I think it's probably so baked in from the kind of densities of it, but I will take that one on notice. I know many pulsar astronomers, and I will ask them that. Thank you. It's a good question.
Thank you very much, and thanks, Jo, again.